approach. Many thanks, Maciej. Please, the floor is yours. The screen is yours.
Thank you very much, Karol, for introduction, and thank you very much, KCIK, for inviting me here. So as always, I start with all these logos of the organizations that support my research at ICFO. In Castel-de-Fels, I will be talking about Bell inequalities from many-body systems, from dynamical programming to data-driven approach. I don't know if I will have time to talk about dynamical programming, but I will. If not, I will skip some parts. That's it. So having many sources of research allows to have a huge theory group. I have 10 postdocs maybe and about 15 PhD students. There are even some experimental people working in the group. There is even a composer working on incorporation of quantum randomness into compositorial processes in contemporary music. So it's very broad. And this is the photo from the last Christmas party, which was in 2019. So it's not very actual, but still. The attitude is still as enthusiastic as you can see. So the outline is I will give you the introduction to Bell inequalities, even though probably all of you are experts, but I will do that anyway. I will then talk about the permutational invariant Bell inequalities, which is it goes back to 7 years old projects done in ICFO. Then I will, if I have time, I will talk about energy as detector of non-locality in many-body systems, where I will use dynamical programming. And finally, the main subject is the newest paper on many-body Bell inequalities driven by, from average to body correlation, but driven by the experimental data. Okay, so introduction to non-locality. Funny enough, the slides that I'm using are the slides that have maybe 8 years, and they are the slides from the PhD defense on Anna Belen science, who is in Gdańsk currently. This was the set of papers that she and Jordi Tura initiated at those times, working on exactly non-locality in multipartite quantum systems, but better to call it maybe Bell correlations in many-body systems, and I will explain it why in a second. So, wrong button. So in a contemporary approach, when you talk about non-locality and Bell correlations, you consider the device-independent description in which you have a set of parties, have black boxes. The parties choose their measurement observables, x1, xn, and they have outcomes a1 to an, and therefore everything is coded in the conditional probability under the assumption that the parties chosen the observable x1 to xn, and they get the outcomes a1 to an. Everything is there. So typically we talk about this kind of NMD scenarios with n parties. Each party has m choices to measure and the outcomes for each choice, which of course can be generalized to more complicated situations. Now, in this kind of world of correlations, there are two which are particularly important: the classical or EPR correlations, which essentially are the ones described by the local hidden variable theories. So if I would know the local hidden variable lambda, which could be, of course, not one number, it can be 1017 dimensional vector or something like that. If I know lambda, however, then everything is deterministic. If the first party measures observable x1, there is an outcome a1. One of the outcomes is with the probability 1 and all the others with 0. So everything is deterministic. The only correlation or the only statistical aspect comes from the fact that I don't know the hidden variable lambda, and therefore I have to average over the unknown probability distribution of those lambdas, and this gives me correlations. The other set of correlations which are important are quantum correlations, which are given by the standard formula that we know from quantum mechanics. You have a set of measurement operators here. I take the von Neumann, so they are orthogonal, but they can be generalized, doesn't matter. I have some Hilbert space in which I have a states described by density matrix, and my outcome and my probabilities, conditional probabilities, are given by this trace formula. The classical probabilities form this polytope, obviously, because we know even what are the extremal points, because they are described exactly by this deterministic probabilities. So this is represented here by the trapezoidal shape. The quantum correlations go out from this trapezoidal shape, and this is what Bell proven in the 60s. Okay. So what are the Bell inequalities in this picture? These are the hyperplanes that in a sense separate the classical correlations from the rest of the world. Particularly interesting are tight Bell inequalities, which are exactly like what we call lapas in Mediterranean Sea. These are this kind of guys who have a muscle and they stick on the rocks very strongly that you cannot take them out. So these are the tight Bell inequalities. If you have an example, two parties, two observables, two outcomes, you can describe everything with the help of 8 probabilities because the probabilities fulfill certain constraints, including no signaling, including the sum of probabilities equals 1, and so on and so on. And then the example of Bell inequality is the famous CHCS H inequality, which bounds some combination of these probabilities. This is for, again, 2 parties, 2 observables, and 2 outcomes. You can express everything in terms of correlators, which is maybe more known, because in particular the CH SH inequality has particularly nice symmetric form. The correlators of this form, which are average values of this up, down, down, if you think about the spins, these guys summed with 1 minus sign are bounded between -2 and 2. Okay. Oops, again, not the not. Now, what happens when you go to many body systems or many parties? Well, if you think even about 2 outputs, dimension of the space suddenly starts to grow exponentially. Why? Because each party can make m measurements or make no measurements. This is to the power n. I subtract 1 because no measurement by everybody is stupid and not interesting. And this is still a huge number. The number of vertices in this polytope is then number of choices of deterministic strategies. So it is 2 to the power n parties times m choices of measurement. So it's very complicated to do it. And it's even proven that it is an anti-hard problem to characterize Bell inequalities in higher dimensions. So what can we do? And one of the things that was proposed exactly in the PhD thesis of Anna Belen and of Jordi Tura is to use symmetries, okay? But not only symmetries. The first thing was to neglect high-order correlators. Many of the Bell inequalities that we know from literature involve high-order correlators, which are typically difficult to measure in atomic systems or in physical systems. It's not impossible to measure them, but it's very difficult. So experimentalists very much prefer to measure low-order correlators like single particle or 2 particles correlation functions. And then this is a big thing, because if we reduce our Bell inequalities to be described only by these low-order correlators, like up to 2nd-order correlators, then the dimension of the space reduces from exponential to polynomial. Still, if you have 100 parties, it will be of the order of 100 times 100, which is a very big number for practical uses. But it's a big progress. What can you do then? And then you can introduce symmetries. So the things that we have been investigating 7 years ago were permutational invariance. So everybody is equivalent to everybody, or translational invariance. So you put some geometry for the system, for instance, on the ring, and you assume translational invariance. And then, of course, everything simplifies. In particular, if you talk about permutational invariance, and you allow for 2 measurements and 2 outcomes, then the whole Bell inequalities can be parameterized by 6 numbers, essentially. 5 numbers that tell you about the single particle measurements of your observable, and you take two possible observables on a single particle level, so like spin directions, and correlations of the observable with itself, observable with another observable with itself, or intercorrelation. And then this is bounded by some classical bound, which is denoted here BC. Okay, and this now dimension of the space is 5, and the number of vertices is still very huge, because if n goes to infinity, it goes like n squared. But this can be, all these Bell inequalities can be parameterized exactly, and this has been done in the PhD thesis of Anna Belen, and Jordi. And this inequality, this is example of one of those inequalities that they derived in those times, which corresponds to measurements, say, of the spin variable, spin 1/2, sigma z, and another component of the spin in the rotated direction in the place, in the plane spanned by sigma z and sigma x. And if you look at how this, if you look how these inequalities can be violated in practice, well, you see, first of all, that quantum violation is can be quite big. It doesn't go to 0 when the number of particles goes to infinity. So they are robust in a sense. They can really be proposed for experimentalists to be measured. Also dependence on this rotation angle here. So whatever you measure, of course, there is an optimal angle, but if you are close to this optimal angle, if you are close to this optimal, you don't have to be exactly in optimal. The quantum violation occurs in large, regime of all these angles theta. This is just one example. We have parameterized many families of these inequalities. There are Hamiltonians that have ground states that violate this type of Bell inequalities. One is the Slipkin-Meshkov-Dick Hamiltonian, which is known in nuclear physics, but it can be realized with ultra-cold ions, for instance, or with the nowadays with the Rydberg atoms. Okay, it has a Hamiltonian, which is strange because it has everybody with everybody interaction. So it's exactly designed in a sense to the states which are permutationally invariant, or to the Bell inequalities which are permutationally invariant. And this is indeed the story. The ground state of this Hamiltonian is the famous Dickey state, but I don't want to go to details, but it violates some of these Bell inequalities. Another interesting thing, of course, about these Bell inequalities, which are designed by the permutationally invariant quantities, is that you can express the quantities that enter into these inequalities by the total components. If you think about spin, total components of the spin in direction, let's say z, in some other direction, and the quadratic fluctuations of the spin observable. So z squared, or this s1 squared, so to say, or the correlation between z and this spin component in the other direction. So this is obviously inviting experimentalists to measure, because these are the things that you can measure in various systems. One example is spin or Bose-Einstein condensates, and this is what the Basel group has done immediately after we proposed these Bell inequalities. Here you measure indeed the total spin components in the spin or gas, in which you have atoms of spin 1, and in the collision 0, 0, you create state plus minus 1 plus, and you create squeezing, essentially entanglement, pair entanglement, but also squeezing. And this squeezing is then detected by this Bell inequalities, or leads to violation of these Bell inequalities. Okay, the one comment is here, obviously, that this kind of demonstration is not the demonstration of non-locality. This is microscopic system in which, of course, the non-locality loop is not closed. So if you want to talk about philosophy, you go to the philosophy department. Here, we are characterizing the properties of the quantum many-body states. And of course, however, if the state violates these Bell inequalities, then this is a certification that it is entangled. So this is like witnessing entanglement with this, guys. But I cannot claim that we measure non-locality here. That's why I prefer to talk Bell correlation. There are other ways of measuring this kind of total or global quantities like total spin correlations, and even more. For instance, using a so-called spin polarization spectroscopy or quantum Faraday effect. This is typical for atomic ensembles. So it can be cold atoms, but not ultra cold or ultra cold atoms. And you essentially shoot light through it, and the polarization of light turns the spins of atoms. Then you read the light, and from this you infer about the properties of the total spin of atoms and so on. And as I'm saying, Rydberg atoms are another platform. There are more. Okay. So as I'm saying, this approach is not for non-locality, but it's more like about the entanglement witnessing. But interesting thing is that the violation of this Bell inequalities not only tells you that the state is entangled, but also characterizes the nature of entangled to some sense. In particular, if you think about the concept of the states which are K-producible, so K-producible means that most K particles are entangled. So for instance, 3 producible states would have a groups of 3, but not a group of 4, and genuine 4 entangled particles. And then indeed, the more you value moreover, will be accessible to measurement, because it will correspond to some physical quantities. And that was the idea behind this paper. So here we consider Hamiltonians, which correspond to one-dimensional. I mean, it can be done also in, let's say, quasi-two-dimensional ladders and things like that. But let's focus on 1D. So these are spin chains. You have a local magnetic field, if you wish, term, multiplying sigma z, and you have some of the spin-spin interactions involving string operators, which have this form: sigma x here or sigma y, sigma x or sigma y here, when separated by the product of sigma z's in the middle. Why do we take? Well, because this kind of spin Hamiltonian under Jordan-Wigner transformation transforms into a quadratic fermionic Hamiltonian. So it's essentially exactly soluble in the sense of I need to diagonalize one big matrix, but not too big, and that's it. So in particular, in the family of this Hamiltonian, there are standard two-body spin-spin Hamiltonians in which nearest neighbors of spins are interacting, and they are also in some transverse or not necessarily transverse in some magnetic field. So these are the Hamiltonians that are obviously realized with the many systems, from ultra-cold atoms through ions, through Rydberg atoms to God knows what. And the Bell inequality now that we want to construct is simply based on this Hamiltonian. So the Bell operator should correspond to the Hamiltonian plus the classical bound. So of course, the classical bound is calculated as minimum overall local hidden variable of the quantity I, which is essentially the value of this energy, but in terms of classical variables. And if it happens that the quantum ground states has the energy smaller than the classical one, then this is the situation in which the Hamiltonian serves, or this Bell operator built from Hamiltonian, serves as a Bell inequality, and moreover, we find the state that violates this Bell inequality, which is the ground state of this Hamiltonian. Okay, so this energy expressed in terms of these measurements and so on has this kind of form. I'm not going to go into details. Again, by Fine theorem, we can replace the averages of the classical measurements by the products, in the case of spin 1/2 or binary measurements, by the products of deterministic results that can be plus minus 1 and so on. And therefore, finally, this classical bound is given by minimum over all possible choices of these plus minus 1s of the quantity I, which corresponds to, let's say, classical energy of local hidden variable. Okay. And now the point is that when you look at you can introduce this quantity here, which is essentially the difference between the energy calculated up to the ith level and I to level I minus 1, and the energy calculated up to level I. So this is in particular this concept of this energy calculated up to the side I, from the right to the from the left, sorry, to the right. And this energy at I is given by the one that was before plus this correction which I have defined here. Again, technicalities are not important. The point is that when you optimize this with respect to classical things, what happens is that the part that was for I smaller than I minus 1 are fixed because you optimized it on. So the optimization process in this next step is really involving only 3 layers, I minus 1, I, and I plus 1 for the Hamiltonians with nearest neighbor interactions. If there are longer range interactions, it's a little more complicated, but we also did it recently. Okay? And this is wonderful because essentially you do it exactly by this dynamical programming. You optimize this, then you go to this one, you optimize this line by fixing, keeping those fixed, and then you move and move and move to the right. And the results are interesting because, of course, you can apply this, you can apply these techniques to the permutationally invariant Hamiltonians. You will get similar things that we get before. Translationally invariant, you will get things similar that we get before, but now you can do it for systems that are bigger than just 8 parties. But you can also apply to something which is without any symmetry. So here is a picture from one-dimensional spin glass. So the couplings are random. So they have no translational and no permutational symmetry. And nevertheless, here above this wine line, so this is like chemical potential, and here I don't remember the strength of, I don't remember what is the, this is so anyway, above the white line, in this spin glass model, you get the regime in which you violate, in which the ground state of the Hamiltonian violate the Bell inequality defined by the Hamiltonian, and moreover, it happens on average for arbitrary realization of the disorder, because this result here is average over 1,000 realization of the disorder, if I remember well. Again, on the axis here, I think this is the strength of disorder. This is a chemical potential, which essentially controls how many spins are, how many are done. Let me go now to the main part, which is the recent paper. Many-body maybe is from average two-body correlation. So the point will be now, okay, so we have designed some bells with the Hamiltonians, which are not translationally nor permutationally invariant. Now we come back to permutationally invariant, but driven by the data. And this is the main achievement. So how does it work? Well, imagine you have a knowledge of data, and data which are exactly, if you have individual possibility of measuring individual, say, spins, you have individual spins, components, squares of these components, if this is not spin 1/2, but 1, for instance, correlations with the spin components, and so on. Now, if you have this data, you symmetrize it, or if you wish, you make from the very beginning work with the data, which is a total spin component, total square of spin component, and total correlation. I mean, whatever, you either measure individual or you from the beginning have access only to these global quantities. And now you try to construct the Bell inequalities based on these quantities, which you get from the experiment. So these are data-driven things. And now you write down the Bell inequality. It should look like that. So you introduce some arbitrary matrix, which we will assume is positively defined. You take the correlation matrix, but look, this is interesting. You take not just this correlation, which is defined here, but you subtract the single particle part. So this is like cumulant matrix rather than just correlation matrix. And then, well, you add some linear terms, so vectors multiplying this, so to say, local observables summed over I. And then this plus the beta classical should be bigger than 0, where, of course, this beta classical is a classical bound on the energy. Okay, so to compute the classical bound, again, we can use the Fine theorem, and we can replace all these classical averages by plus minus ones, or in the case of the spin J, by the numbers between minus J and things like that. And the energy then is expressed in this form, and where A, if we assume that A is positively defined in this formulas, or semi-positive, semi-definite positive, then this is bounded from some maximal energy, and we can prove that it is smaller than this classical bound. In fact, usually these two things are equal. At least in all examples that we have been calculating, they were equal, but just to be formal, I keep the smaller equal, doesn't matter. But anyway. And this is independent of this problem. And therefore, the problem of finding these guys in the matrix semi-definite and the vectors H1, H2, such that this thing is smaller than 0 can be expressed as semi-definite programming problem, because this function is convex. And this is what we really do. So we try to minimize and so on. And then there are two possibilities. Either it is feasible to find the minimum, and then it means that nothing happens, but it might be unfeasible. So for some of these choices, this L becomes negative and becomes unbounded essentially from below. And that means that the data must descend from the quantums, from the entangled state. You can somehow regularize it and things like that. I don't want to go to the details, but the point is you use semi-definite programming to check whether from your data and from the designed Bell inequalities, you can invoke that your state is entangled or not. Again, all these things, I remind you that since we are talking about the quantities which are averaged over which are essentially made permutationally invariant, yes, because I sum over all contribution of local spins. So this is the total spin component. I sum over all contribution of square of local spins. So this is a nematic, global nematics parameter QAA and things like that. And correlators is also expressed in terms of nematic parameters and covariance of the spins and things like that. So these are things that are measurable by many methods in many body systems. And I will just tell you something about the results now. So to illustrate this method, what we did, we just considered some states, which we know how they look like. We generated randomly the data corresponding to these states from some design measurements, and then we derived the Bell inequalities corresponding to these things. And then this kind of approach, first of all, we have recovered the two outcome permutationally invariant Bell inequalities of Jordi and Anna Belen, and even improved them. I will tell you in which sense. We have made we have derived a lot of PBs, as we call pi bias, I don't know, PBs that are tailored to spin squeeze states of arbitrary spin, not only spin 1/2, which was done exactly before and which was measured in Basel, but now we are talking about the generalizations. And finally, we have derived inequalities tailored to spin singlet states. So states in which the total spin is 0. And essentially, so for spin 1/2 and particle states with mean spin like that, we consider the two measurements with the sigma z and sigma, in this case it was sigma x and sigma y mixed with sigma x. And then we recover indeed Tura and Belen inequalities from signs. Again, this has this form. I don't want to go to the details because you have to go yourself if you want to really use it. But the interesting thing is that in the inequalities that we derive, the correlation matrix C, which is appearing in the Tura inequalities, is replaced by this nonlinear form, which is the cumulant. So C minus the single particle averages of the quantities that enter there. And now this is of course nonlinear. So if you look at the classical polytope, then Jordi's inequality is hyperplane. So it separates from the classical correlations from the rest by hyperplane, but now we have nonlinear thing, which obviously is better. It separates much more states and detects much more states than the original inequalities. Okay, so these are the two examples how it more or less looks like. For the spin J and particle states and squeezing again, we can find out the permutationally invariant Bell inequalities, which are especially designed to measure this kind of squeezing with the spin J, and then you get a witness, which is relatively simple. Again, to measure in experiment, this is generalizing again Tura et al. And you can even make more robust inequalities by adding to this approach more of measurement. This approach is very general. It works for whatever number of measurements you want and so on. It's of course technically more difficult to do the semi-definite optimization and things like that, but in principle, this is how it works. So this is example of spin J and particle state. Now the last example is about the singlet, So the singlet is a spin J and particle state with average value of J0 and of course average value of J squared 0. So it's really a total singlet. So there was some knowledge about this kind of detecting this kind of states for J equal 1/2, so singlets of many spin 1/2 states. But now we generalize this and derive things for arbitrary J, essentially. And we do it for, well, we have to choose what measurement we take. We take coplanar measurement, so we have to, we measure the spin components in 3 directions that lie in the same plane. And therefore, there are 2 parameters to characterize everything. We choose U3, let's say, to be a Z component, and then UA times U3, the cosine of this angle, since you have 2 directions here, so you have 2 cosines of the angles of parameter T1, T2, and this is how you parameterize. And then what you get is really, you can get families of Bell inequalities, which often are equivalent, but anyway, this is the plane in which you plot this T1 and T2. So this direction of this coplanar vectors in which you do the measurements. And for spin 1/2, you have essentially 1 family, which is again related to the Tura original paper et al. But for spin equal 1, you already have 2 non-equivalent families, which we call 2, 3. In spin 3/2, there are actually 3 families that contribute. So each of this region in which you have blue means that you have a violation of Bell inequalities, important. And then as you go to higher spins, you have more and more non-equivalent families of Bell inequalities. that are designed for this kind of situations. And I think that I will conclude. Bell correlations, as I say, are not equivalent to Bell non-locality, because in all these experiments with the many-body systems, you don't close the locality loop. You measure global quantities, but you can characterize the system anyway. So it's not Bell test, it's not this, but it characterizes detect the nature of entanglement in the system without assumptions on the state and Hilbert spaces. So this is very useful, especially in the context of modern quantum technologies. It's flexible, experimentally friendly, and data-driven algorithm to obtain this Bell inequalities violated by average correlation. So you have the experimental results, you can check it immediately. It recovers all known permutationally invariant Bell inequalities violated robustly in the thermodynamic limit. And we discover new ones tailored for paradigmatic states. At this moment, we can check all states, but there's a huge open space to study more. And then, in a sense, these are we have a derivation of Bell correlation witnesses of broad applicability, as my student Guillaume Regat says. And this is a list of papers on all these Bell inequalities business, starting from the science in 2014 of Jordi and Anna Belen and Remick, of course. And this goes, I mean, these are papers, I think 12 papers, including the last one that I was reporting in this talk. There is another one in which we mix the things with the machine learning and things like that. Most of the papers here are me as co-author, although there are more which I'm not a co-author. Probably Remick knows more, but one nice paper here by Irene Frero and Thomas Orostilde. If you are interested, you should look. I finish as always with my quantum narcissist. So there is a new book now. Oh, sorry. I have a new book, which is the Amateur's Guide to Avant-Garde, Catalonia, Poland, Portugal, and more, should appear on Bandcamp next week. So if you are tired, you should look into it. Thank you very much for your attention.
Maciej, thank you very much.